1993, Iana Salvador of Italy walked 3 kilometers in under 12 minutes. Well, that's very good for him. Suppose that during 115 meters of her walk, I guess it's a lady, Salvador is observed to steadily increase her speed from 5.2 meters per second to 5 meters per second. How long does this increase in speed take? Or assuming that we have the same pace going on here, we have an initial velocity of 4.2 meters per second, and we have a final velocity of 5 meters per second over 115 meters. Our equations, we know that our average velocity is equal to delta t, or delta x over delta t. And we also know that the average velocity, when we have two velocities, is our initial velocity plus our final velocity divided by 2, taking the average of that velocity. All right? Seeing as we're given a distance and we're given 2 velocities at a constant acceleration, we can determine that our average velocity, vi plus vf, divided by 2 is equal to our distance over our time. Or, using algebra, once again, we see that they give us the equation delta t is equal to 2 times x divided by, flip it over, crisscross, vf plus vi. Taking our numbers, 115 meters for x, 5 meters per second for our final velocity, plus the 4.2 meters per second for our initial velocity, we can plug, chug, and crank out our answer. Go ahead. Take your time. Is everyone caught up with me now? All right. Question number 2. Let me erase this here. All right. In a scientific test conducted in Arizona, a special cannon called HARP, High Altitude Research Project, shot a projectile straight up to an altitude of 180 kilometers. If the projectile's initial speed was 3 kilometers per second, how long did it take the projectile to reach its maximum height? We're given an initial distance from the ground all the way up to the top, 180 kilometers. The initial velocity given to us, our VI, is 3 kilometers per second. 3 kilometers per second. Our final velocity, or the velocity that it's at when it reaches its peak distance of 180 kilometers, is going to be 0. Because we know what goes up must eventually stop due to gravity and then come back down. So the maximum height is 180 kilometers, and this is the point that it actually stops rising into the air and then starts falling back down. The time that we're going to find is our unknown. We could change this, we'll convert it automatically to 0 kilometers per second instead of meters per second. Now we're given in kilometers, and we're given in kilometers. We're going to look for time in seconds. Do we need to convert kilometers all the way to meters just to determine what the seconds are? No, we don't. You'll see if you put in here, if our x is 180 kilometers and our VF being 0 plus our VI, 3 kilometers per second, when you have kilometers per second and kilometers, we need to reverse this. So we have up here kilometers times seconds divided by kilometers. Our kilometers will cross out, and our time will be given in the unit of seconds, just like we wanted. X, 180 kilometers. VF, 0 kilometers per second. VI, 3 kilometers per second. Go right ahead. If you don't believe me, you can convert this to meters, or multiplying by 1,000. You can convert this to meters per second, multiplying by 1,000, and see how the 1,000 you multiplied by here divided by the 1,000 you multiplied by there cancels each other out, and you get your answer just like you would before. Take a second and try it if you don't believe it. Question number 3 says, the fastest speeds traveled on land have been achieved by rocket-powered cars. The current speed record for one of these vehicles is about 1,090 kilometers per hour, which is only 160 kilometers per hour less than the speed of sound in air. Suppose a car that is capable of reaching a speed of 1.09 times 10 to the third kilometers per hour is tested on a flat, hard surface that is 25 kilometers long. The car starts at rest and just reaches the speed of 1.09 times 10 to the third kilometers per hour when it passes the 20 kilometer mark. They've used a lot of numbers in here. Our initial velocity, to be sure though, will be 0 kilometers per hour because it's starting from rest. The maximum speed it's going to reach is 1.09 times 10 to the third kilometers per hour, which once again is just a fancy word or name for 1,090 kilometers per hour. And the distance traveled is 20 kilometers, not 25. It just passed the 20 kilometer mark. The last sentence is the most important sentence. The car starts at rest, 0, reaches a speed of 1.09 times 10 to the third kilometers per hour when it passes the 20 kilometer mark. Our distance is 20 kilometers. What is the time that it's going to take? If the car's acceleration is constant, how long does it take to reach the 20 kilometer mark? 2 times x divided by VF plus VI will give us a time in hours. Kilometers, kilometers, kilometers per hour will give us an answer in how many hours it will take for this to reach, or what part of an hour it would take. You can convert this to seconds by multiplying, by taking your hours and having 1 hour conversion factor is 3,600 seconds, so that hours cancels out. So you multiply by 3,600 and you'll end up with the amount of seconds that it takes if you wanted to do that. How long will it take the car to decelerate if it goes from its maximum speed of 1,090, so this will be its initial speed, to rest? Its final speed will be 0 kilometers per hour. So we've just reversed that. Our initial speed now is 1,090 kilometers per hour. Our final speed is 0 kilometers per hour. If it does this in the remaining 5 kilometer stretch, 5 kilometers. All right. So now we have a time. We have x is 5. So 2 times x divided by our VF0 plus our VI of 1090. Once again, you have kilometers, 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 hours, hours. Your answer will be in hours. If you would like to know what that is in seconds, you could use your conversion factor. Of 3,600 seconds over 1 hour. But that isn't necessary for these questions. Only if you're curious, you can do that. Once again, just like in the last section, if you need to pause the tape, the first flight around the globe without a single refueling was completed. The aircraft's average speed was 186 kilometers per hour. If the airplane landed at this speed and accelerated at negative 1.5 meters per second squared, how long did it take for the airplane to stop? So we have an initial velocity is equal to 186 kilometers per hour. We have a final velocity of 0 kilometers per hour, or meters per second, 0 meters per second. It converts very nice, I know. And an acceleration of negative 1.5 meters per second squared. Negative 1.5, meaning that it is actually decelerating. Negative acceleration is slowing down, or deceleration. And we're looking for how long did it take, our time, question mark. All right, we're given quite a few equations over here on the previous page about finding time when we're given an initial velocity, we're giving a final velocity, and we're given a acceleration. So let's take a look at what we have here. Acceleration is equal to delta V over delta T. Our change in velocity is equal to our final velocity minus our initial velocity over our time. So if we're looking for the time, we use algebra. T is equal to VF minus VI over our acceleration. We're looking for T. We're given a VF. Sorry. We're given a VI, and we're given an acceleration. Now, obviously our VF can easily convert into meters per second. We need to convert this once again from kilometers per hour into meters per second. And then we'll end up with a time in seconds and not hours. So to do this, since our acceleration is in meters per second squared, we want to use all the same units for our quantities. 186 times, we have in 1 hour, 3,600 seconds. So 186 divided by 3,600, find an answer. And then times, we have in 1 kilometer, we have 1,000 meters. So 186 times 1,000 divided by 3,600, 186 divided by 3,600 times the law of equalities here. We'll get it. Either way we get it, but we just solve out this to find what our initial velocity is. And notice that our VF is 0, which means our initial velocity, although it was positive, has now become negative, and our acceleration was already negative. So don't forget that a negative over a negative is a positive. And that's all you had to do for this first problem. Let's look at where we got here, problem number 2. Did you feel that? No? Okay. So let's take a look at problem number 2, just like I was saying a second ago, before I got that really weird feeling and something's different. Okay. So in 1976, Gerald Hoagland drove a car over 8.0 times 10 to the 2 kilometers in reverse. That's basically 800 kilometers. Fortunately for Hoagland and motorists in general, the event took place on a special track. During this drive, Hoagland's average velocity was about negative 15.0 meters per second. Suppose Hoagland decides during his drive to go forward. So he applies the brakes, comes to a stop, and then accelerates until he moves forward at the same speed he had when he was moving backwards. How long would the entire reversal process take if the average acceleration during the entire process is plus 2.5 meters per second squared? All right, so when we look at this problem, we can break it into 2 parts. All right, so let's write down what's given to us. All right, so we're given an acceleration of plus 2.5 meters per second squared, and we have an initial velocity of negative 15.0 meters per second, and we're going to come to a stop. So we have a final velocity of 0 meters per second. All right, so when we set this up, we're looking for the time. So our equation that we've been using, acceleration is delta v, or change in velocity, over a time interval, and our change in velocity is our final velocity minus our initial velocity, and that's over a time interval. But we're looking for the time interval, so we're going to multiply both sides by t. So we get t and a on one side, and our final velocity minus our initial velocity. And if we divide both sides by the acceleration, then our equation that we can use right now is that the time that we want is our final velocity minus our initial velocity over our acceleration. Okay? So what we have taking place here is we have a final velocity of 0. All right, so our time, we have a final velocity of 0 meters per second, and then we have that minus a negative minus 15.0 meters per second. And that's over an acceleration of plus 2.5 meters per second squared. All right, so all you have to do is a negative and negative, they cancel out, and they form a positive. So all we have is that our time that we're looking for is 15 meters per second divided by 2.5 meters per second squared. Right? And that's the time it takes for this car to go from going backwards to coming to a complete stop. Now, if it continues in the same motion to get back to speed, you'll see that the second part of the problem will mirror your equation that you're using here, and in that instance, all you have to do to figure out the entire time that it takes is whatever this answer is right here, times 2, gives you your final answer. Okay? So that's all you had to do for your problem 2D section 2, question number 2. All right, so let's go on to our final 2 problems on problem 2E number 1, and then we have 2E number 2. So I'll click this and we'll look at 2E question number 1. It says, in 1976, Kitty Hamilton of the United States drove a rocket engine car to a maximum speed of 965 kilometers per hour. Suppose that Kitty started at rest and underwent a constant acceleration with a magnitude of 4 meters per second squared. What distance would she have traveled in order to reach the maximum speed? All right, so we're given some problems here, and if we're given an acceleration and we're given a initial velocity and a final velocity, and we're looking for distance, then our sample problem tells us how to use this equation up here. So let's write down what we have. So we have an acceleration which equals 4.0 meters per second squared, and we have an initial velocity. All right, suppose she started at rest, so her initial velocity is 0 meters per second. And when a constant acceleration to reach the maximum speed, so our final velocity is 965 kilometers per hour. All right, so these are the 3 variables. We're looking for our horizontal displacement, which is x, okay? And the equation that's given to us in our problem sheets right here is that x equals our final velocity squared minus our initial velocity squared divided by 2 times the acceleration. All right, so this is the equation that is given to us in our problem. And that equation was originally rearranged algebraically from the equation that we can find on our New York State reference tables, which is that our final velocity squared is equal to our initial velocity squared plus 2 times acceleration times the distance. So it was rearranged for us, and it shows those steps on our sheet. So the equation we're using is x is equal to vf squared minus vi squared divided by 2 times the acceleration. All right. So one of the problems we have here, though, is that this is meters per second squared, and this is meters per second. This is in kilometers per hour. So we're going to need to use our conversion factors of that there's 3,600 seconds in 1 hour, and there's 1,000 meters in a kilometer, to determine what this would be in meters per second. So I'm going to do this 2 steps, all right? So we have a conversion factor that there are 3,000, all right, messed that up. We have a conversion, so we're going to do this in 2 steps. So we have a conversion factor that there are 3,600 seconds in 1 hour. And then hour and hours canceled out, so you have kilometers over seconds. And we also need that there are 1 kilometer as 1,000 meters. Okay? So we have 965 kilometers times 1,000. Kilometers cancel out, divided by 3,600 seconds. And that'll give us a final velocity for this problem, an answer of 268 meters per second. 268 meters per second is our final velocity. So, what we're going to do in this problem is we're going to take our VF, 268, minus VI, which is 0, and divide it by 2 times the acceleration, which is 4. You can see right away that when we plug it into our problem, that 268 meters per second squared, the whole thing squared, 268 meters per second squared, divided by 2 times 4 meters per second squared, minus 0 squared, right? You can take this right out. You can take out this 0 squared. And all we have to do to solve this problem, to find our distance, is we have 268 squared divided by 8. And that gives us our answer. So that's the answer for 2E, number 1. We're going to find that. So look at it. Our last problem is 2E, problem number 2. And it says, with a cruising speed of 2.3 times 10 to the third kilometers per hour, the French supersonic passenger jet Concorde is the fastest commercial airplane. Suppose the landing speed of the Concorde is 20% of the cruising speed. If the plane accelerates at negative 5.8 meters per second squared, how far does it travel between the time it lands and the time it comes to a complete stop? All right, so let's write down what we have here. We have an acceleration of our Concorde that's given to us as negative 5.80 meters per second squared. And we have a final velocity as it comes to a stop is 0 meters per second. Our initial velocity is 20% of the cruising speed. So our cruising speed is 2.30 times 10 to the third power, and 20% of that would be times 0.2 to find our initial velocity as it came to a landing. All right, so let me put that in my handy dandy calculator here. 2.3 times 2300 times 0.2 equals 460. All right, so 20% of that would be 460 kilometers per hour. All right, so this was given to us in kilometers per hour. Once again, in order to solve this problem, we're going to have to change kilometers an hour to meters per second. So we use our conversion factors, 460 kilometers per hour. And we have 1 hour is 3,600 seconds. And our next conversion is that there's 1,000 meters in 1 kilometer. So you see that kilometers and kilometers cancel out, and we see hours and hours cancel out. So we're stuck with 460 times 1,000 divided by 3,600, and we get 127.7 repeating. So we can put in here 128 meters per second. So our initial velocity is 128 meters per second. All right, so we're looking for the distance it comes to. We're given the same equation. All right, so our original equation given to us on our New York State reference table is that VF squared is equal to VI squared plus 2 times acceleration
times x. And we saw some work done in there that if you have subtract vi from both sides, you have vf squared minus vi squared equals 2 times a times x. And if we're looking for x, we just divide both sides by 2 times a. And this cancels out. So we have x is equal to vf squared minus vi squared divided by 2 times a. So in this instant here, we have our vf is 0, so 0 squared can come right out. So we have minus vi squared, so that's 128 meters per second squared. So we have our, in our problem here, we have x equals minus 128 meters per second. You square that whole thing, divided by 2 times an acceleration of minus 5.80. Actually, the negative's on the outside when you square it, so that you don't lose it. So we'll have a negative answer divided by a negative answer. So we have 128 squared, and that's negative, and then divided by 2 times 5.80, and that's negative. Negative over negative gives you a positive answer. So go ahead, plug it in your calculator, solve it, and you're done for tonight. Have a nice night.